Hello, in this video we take an overview on Berkeley Lower Extremity Exoskeleton, not released for public viewing until November 2007. The Exohiker was the first generation field-ready exoskeleton designed by Berkeley Bionics. The system, completed at the beginning of 2005, has given birth to subsequent generations that have military applications and promise to replace wheelchairs for many patients suffering from mobility disorders. Here, design of the Berkeley exoskeleton. The first field operational lower extremity exoskeleton is comprised of two powered anthropomorphic legs as shown, a power unit, and a back-like frame on which a variety of heavy loads can be mounted. This system provides its pilot with the ability to carry significant loads on back. £100 payload. With minimal effort over any type of terrain. It allows the pilot to comfortably squat, bend, swing from side to side, twist and walk on ascending and descending slopes. Running with heavy loads, there is no problem. In missions that takes long time, it can be easily hand carried. It enables running in emergencies with heavy loads. It also offers the ability to step over and under obstructions while carrying equipment and supplies. The overall concept of this lower extremity exoskeleton is that the human provides an intelligent control system for the exoskeleton, while the exoskeleton actuators provide most of the strength necessary for walking. It has numerous potential applications. It can provide soldiers, disaster relief workers, wildfire fighters, and other emergency personnel the ability to carry heavy goods such as food, rescue equipment, first aid supplies, communications gear, and weaponry without the strain typically associated with demanding labor. The control algorithm was designed to increase the closed-loop system sensitivity to its wearer's forces and torques without any measurement from the wearer. This block diagram shows how the exoskeleton moves the upper feedback loop, shows how the human moves the exoskeleton through applied forces. The lower feedback loop shows how the controller drives the exoskeleton independent of the human feedback loop? The first equation, d equal minus h of v. Positive feedback control is used such that our goal of sensitivity application is achieved. S nu more than S for all omega belongs to 0 and omega node, where omega node is the exoskeleton maneuvering bandwidth and S nu is the closed loop sensitivity transfer function from human torque d and the input to the exoskeleton motion v at the output. S nu equal v divided by d. C equal 1 minus alpha of minus 1 multiply g power of minus 1, where alpha is the amplification number greater than unity. This equation, the 5 equation, simply states that a positive feedback controller needs to be chosen as the inverse dynamics of the system dynamics scaled down by 1 minus alpha power of minus 1. Here, as shown, two tables declare peace and Odessa of the Berkeley exoskeleton, as shown in the tables. If you want to evaluate the Berkeley exoskeleton with the mixed control method, a pilot can walk at half meter per second with a payload of 18 kilograms. Mixed control offers other benefits in terms of robustness to changing payload dynamics. An additional problem encountered while testing mixed control was that the pilot needed to use a handrail to maintain lateral balance or side-to-side balance. Once one leg was in swing, the whole pilot and Bleek tended to fall toward the swing leg in the lateral plane. This was due to, in large part, to the fact that abduction and adduction joints at the hip weren't powered, because the harness was designed to improve the performance of the master-slave control mode. The pilot was unable to apply enough torque compensate for the lack of powered hip abduction and adduction. The pilot was able to provide a small balancing torque through the semi-rigid foot connection, but this was insufficient to provide lateral stability. This was a fast overview on Berkeley exoskeleton. Thank you.